Thank you, team. Now I would like to invite Immverse AI. So some intro about this company. Immverse AI acts as a bridge between ancient Indian wisdom and modern AI innovation, building an AI ecosystem that connects learning, research, manuscripts, and knowledge dissemination through AI-powered conversation platforms and avatars. The team consists of AI professionals, researchers, developers, building AI and ML solutions. May I now invite the team onto the dais?
No problem. All right. So the same introduction, but there was a slide which I guess got lost. So we are working on kind of integrating this ancient Indic wisdom hidden in like manuscripts and integrating it with the modern AI innovation and like making it accessible to the world through conversation platforms as well as like interactive avatars. And so we have built products around that. So things like chat-based conversations and interactive avatars and learning-based platform, which is like AI-powered personal learning. And currently we are also working on domain-specific vertical GPTs for, let's say, healthcare or similar domains. So when I say healthcare, it's like Ayurveda. And for this particular hackathon, so that's our team. I am Pradeep. I am Principal AI at Immverse AI. And Himanshu is VP of Engineering, also a hands-on engineer. I have Pratik and Tushar with me. So they are AI/ML developers and did the heavy lifting for this project. Along with one more member, Pranay, he's like missing here. Right, so starting the problem statement, again, as we know, it's multi-speaker, multilingual TTS for Indian languages, 10 Indian languages along with English, with some additional special feature requirements like ability to do zero-shot voice and style transfer, and like code switching, mixed language input should be handled, and then, of course, efficiency and scalability of the solution, those kind of things. So the approach we decided to go with is, okay, just to, an interesting bit is when we started with the hackathon, that time we were working on a separate model for Sanskrit TTS and trying to deal with the nuances of Sanskrit, but not really gotten into this space of several multiple Indian languages handling through a common model. So here we, given the relatively shorter time frame and also the access to resources that we have, we decided to kind of find the best available resources and kind of leverage it as much as possible and then try to accomplish the goal. So idea was to find a suitable base model that we can work upon, improve upon, and train further for the target languages. Then also integrate the additional features as required for code switching or style transfer and so on, and build like an end-to-end pipeline for this TTS solution. So we selected FI model-based architecture and in turn Indic FI, which is like trained on the same architecture, but trained on some of the Indian languages from our target set. So there are like 6 languages mentioned here. Kind of supports the voice transfer already, but we need to extend it to all the languages. And okay, we'll come to the architecture. Does not really support English at all. So yeah, so in brief, I will like to talk about the overall TTS pipeline architecture that we built. Just to go into the little bit details of the model architecture itself, on the right side, the main key TTS block is expanded. So basically it takes 3 inputs, kind of concatenated text from the reference audio as well as the target text, then the MEL spectrogram from the reference audio, and the spectrogram part of the target is kind of masked, and you have entire Gaussian noise representing the starting point for the spectrogram to be generated. And these 3 are concatenated and provided to, so this is basically a flow matching based architecture using diffusion transformer. So the text part is converted into a representation more refined and aligned with the speech part using the connext 2 blocks. And then all the 3 are concatenated and passed to the DIT block. The diffusion transformer will try to predict the vector fields that will allow for the like basically transfer from the noise Gaussian distribution to the target distribution of the data points for the MEL spectrogram that needs to be predicted. And the audio solver then will convert it into the actual MEL spectrogram. And as you can see, I started with this block because there is some nuances. So what we do is, for the style transfer part, the reference audio and text is already kind of included within the context of the model itself. And then it becomes like a conditional flow matching flows and conditioned on the properties of the audio captured in the MEL spectrogram. And in the generated spectrogram also, this part will remain. So we kind of need to trim that out to get just the generation part, and then use a vocoder to convert it into the audio waveform. For this to happen, we need to do some pre-processing steps. So if you look at the block on the left at the bottom, so we get input text and reference audio, but we also need reference text. So we use like Whisper for ASR. But if you look at this, again, there is like a fixed context window. And so basically a fixed number of audio frames that the model will generate at a time, corresponding MEL spectrogram. And part of it will be taken by the reference audio MELs itself. So if the reference audio is too long, there is not much audio frames left for the target generation, and then the audio could be sped up instead of at a natural pace. So we need to limit that. And the model does not really need much longer reference anyway to capture the properties. So typically 3 to 5 seconds is enough, but the audios during evaluation, they were like more than a minute long. So we introduced a trimming module. What it does is it detects the silence pauses in the reference audio and kind of finds a suitable patch of that audio, about 5 second to 10 second max. And that kind of also takes care of, because of the silent pauses, is kind of independent chunk and not arbitrarily cutting in between. So then text from reference as well as the target text goes through normalization for the currency, dates, and numbers. And then it can move forward to the model, except it kind of works for the phonemic languages, so typically English languages. And the tokenization is like character level tokenization, so there's a vocab for the Indian language characters, but doesn't work on the Roman script. It's not really phonemic. So we do two things. One is transliteration, which is from English to Devanagari. And after that, then the model can work well. But there could be sometimes some errors in the transliteration, or some words are peculiar that it may not handle. Plus, primarily, for example, in this particular use case, there is this medical scientific domain, and that has many terms which TTS models typically may not be able to handle. Even the data set usually don't contain those kind of terms. So we have a lexicon mapping kind of model in between, which takes these all domain-specific terms in English and again maps them to also to their Devanagari more phonetic kind of version. So then the model is able to handle them better in two cases. One is English, another is the mixed language kind of thing, where it could be any language, but the scientific terms will be in English. Yeah, and after all that pre-processing, then the model flow is same. Yeah, the same pipeline is kind of explained here. Okay, so challenges also I think I briefly mentioned. So first was there were only few languages supported, so we had to train on the entire CISPIN and Spike core dataset to add the support for rest of the languages. But English, again, is peculiar. For that, just fine-tuning further is not helpful. So for that, we added this transliteration as well as the lexicon mapping kind of models. And yeah, that's here. Other than that, reference audio constant also I mentioned. So we tried two things. One is properly trimming it around the silent pauses, as well as another thing we tried was denoising, but that kind of takes a lot more longer. So in the final version, the denoising part is kind of left out, need to be worked further upon. This is because it is directly conditioned on the reference audio, so the quality of the reference audio also matters. I mean, it might generate something similar. For noisy, it will generate noisy, but it's better if the audio is clean. Then, yeah, normalization part I touched upon for units and currencies, numbers or symbols. And reference text delimitation, the thing is because we are concatenating reference followed by the target text for which we need to generate the audio, that kind of goes together to the model, and it's like one person saying the whole thing. So voice, style, everything will remain same, but the reference audio and corresponding text could be out of context, something else. So we need to purposefully add some delimiters to separate them out so that the model can still generate the target part cleanly. Training details. So on the GPU side, basically we used this cluster of 800 GPUs for 3 days. So we booked on AWS, and the main training was ran on this particular setup. Other than this, we ran many experiments and like slower training runs on a L40S GPU, which we had access to. Data is primarily the Syspin and Spycore. Along with that, we added some open source datasets for Indian English accent, and 400,000 plus training steps, and so some hyperparameters that we basically use the L40S to tune. Batch size, that is also another interesting bit. So we tried to decide the batch size using the audio samples, but some samples could be much longer or shorter, and then it will basically go out of memory, out of the CUDA VRAM OM issues. So then we decided to basically select the audio frames because that kind of is fixed, and that allowed us to efficiently use the GPUs during training. On the evaluation side, so we did all the metrics as expected in the report as well. I'm showing here the MOS and word and character error rates. For MOS, so we took help from the native language speakers that we knew of and provided them with the access to like the reference audio, reference text, the generated audio text for which the audio to be generated, and some guidelines on how to basically score 1 to 5, and that is where we kind of to get a feel of subjectively how the generated audio sounds like. WRCR, for that we just use again Whisper for ASR, and computed this using the standard packages. There were some issues like earlier also mentioned by the team for transcribing using ASR Whisper, but also if the input has like code switching, mixed language, or because of the some like part of the text is or one of the text pairs was normalized and others not. Those kind of issues were there. We kind of realized it late, so we haven't redone the WRCR computation. So there are many things to be improved. So some of them are mentioned here. So on the reference audio side, because we are directly using it for conditioning, that helps to capture the characteristics of the reference very well. But then also there is a lot of dependency on that. So we need to ensure like removal of background noise or robustly trimming the audio to the desired length. There is also normalization works well, but in some context we were facing issues, so that is also something to be improved. For ASR, we are just using faster Whisper, which takes more VRAM than our model. So we need like more efficient and probably India-specific ASR, Indian language-specific ASR modules as well. Punctuation is interesting bit that we figured out. So if you just provide the text without any punctuation, then it will speak it normally. But if you add like commas and delimiters properly, then it does the pauses properly or exclamation and those kind of things. So because that was part of the training text as well. So in case the provided text doesn't have it, automatically inserting punctuation is also something that helps. It's not automatic right now, but we tried with manually inserting the punctuation. Streaming DTS part, also something we haven't implemented in the version that we have here right now. But that is something we have worked on before for other models. So that we plan to do. And model optimization. So currently it's just PyTorch, for example, version format of said model. So we need better compression as well. And there are things like Onyx and TensorRT that we need to look into. One more thing is the speed control. That is something we already tried. It's possible in the model, configurable. That way, given the reference audio and characteristic, but we should be able to also like speed it up or make it slow down. But that's not yet implemented, but something we have already explored. So that is we plan to do. Okay, so there is a demo URL if we want to see, or you want to search? Can we? No. Later? After? Oh. So I guess we can check it later as well. Thank you. Thanks.
So just want to understand the contributions, if I understand correctly. So you took a model that already supports a few Indian languages, and you trained it on the ones that it doesn't support, right?
Right.
And then you also did the transliteration from English to Devanagari so that you can support English as well in the same sort of framework. And then the text normalization bit that you added, and also the evaluation part, right? So that's essentially, so architecturally, was there anything that you did that was different from what was already supported?
No, the core TTS block that we had on the right, that is same as FI architecture.
Right.
And only the pre-processing, post-processing bit, that is where we have done the modifications and the training part.
You talked about better ASR will help for Indian language. Can you explain why?
So basically, in this particular,
what are the characteristic differences? See, Whisper is primarily built with 49% of English.
Okay, so in this context, what I meant is like we are running Whisper. It works for the languages. It consumes like 3 GB plus VRAM. And our model takes much less, like around 2 GB. So that's like additional VRAM if you want to do. And its use is only to get the text for the reference audio.
No, I'm asking you something other than that. For English, for example, the grammatical structure of sentences follows a particular form.
Yeah.
Whereas Indian languages follow a different form.
Right.
And so the language model, for example, would struggle. So can you tell me what that difference is?
Okay, how will it struggle for Indian languages?
I'm asking you, what is the grammatical structure for English versus Indian languages? Because there is a language model which is embedded in the Whisper model, right?
Yeah.
So it could struggle because it's trained with 49% of data from English.
Right.
Tell me what is the difference, at least do you understand it? I want to understand.
I'm not sure very specifically, but so Indian languages have like their own this matras and variation of the characters.
Markers are there in every language.
No, compared to English, for example.
Structural difference which I want to know to understand.
Okay. So I'm not sure then. No. English versus Indian languages.
You studied it in school, subject, verb, object, subject, object, verb.
Yeah.
So that is the fundamental reason why it will struggle. So you're using a square nut and a round bolt.
Okay. Thank you.